Hey, welcome back to the channel. Today we're diving into a very powerful aspect of Zig programming, which is creating data structures that require zero heap allocations. If you're building performance critical systems, embedded applications, or just want a better understanding of memory management, this video is for you. So in most languages, data structures like lists, maps, trees, anything like that is going to automatically allocate memory on the heap. While this is convenient, and we don't have to worry about allocating that memory ourselves, it can lead to performance issues, fragmentation, and really unpredictable behavior when in resource constrained environments. Zig gives you incredible control over memory allocation, allowing you to build data structures that use only stack memory or pre allocated buffers. By the end of this video, you'll understand how to create robust, efficient data structures without any runtime allocations. We'll start with the basic of allocation in Zig, explore fixed capacity data structures, and then build some increasingly complex zero allocation implementations, and some of them are a little too big to really showcase in this video, so we'll just talk through them instead. Let's get started. Before we dive into zero allocation data structures, let's understand how memory allocation works in Zig. So what you see on the screen is the traditional approach. This is allocating memory on the heap, but Zig makes the allocator explicit, unlike many other languages where allocation happens invisibly, garbage collected languages, for example. So you can see here we have a general purpose allocator. We're deinitializing it. We're deferring deinitializing it, and then we are getting a handle on the allocator. Then further down, we're actually allocating space on the heap. So you can see here we're calling allocator alloc. We're passing in a type of I32 that helps know how big the items that we're allocating are, and then the size that we're allocating. So we're allocating space for 10 I32s as an array. The line after that is also used to free that memory when we're finished with it. Heap allocations, when not managed properly, can cause issues like fragmentation over time, unpredictable performance when working with languages with a garbage collector, for example, or even allocation delays, and memory leaks if they're not properly managed. It's one of the nice things about a garbage collector is that they try to help prevent memory leaks for us, but there's a trade-off with those garbage collectors too, right? And if we have full control over memory, we can choose to make our allocations and deallocations work for us. Lastly, heap allocations can also be unsuitable in certain environments like embedded systems or real-time applications. Now, let's look at some alternatives. First, we have stack allocation. Stack allocation is simple and efficient, but it has size limitations. For larger structures, we could use something like a fixed buffer with slices instead. This approach uses the allocator interface, but the memory comes from a pre-allocated buffer. This gives us the best of both worlds, the convenience of an allocator in Zig with the predictability of pre-allocated memory. Now let's build our first zero allocation data structure, a fixed capacity array list. So there's a lot going on the screen right now, and I've truncated some of the methods that you would expect to see on an array list, but you don't actually need them to understand this example. So let's analyze this to see what makes this zero allocation. So the entire structure is allocated on the stack. So if we look at this, we're not taking in an allocator, we don't need any heap allocations, and the items are allocated and stored right here. You notice that we have a variable size, and this is due to Zig's comp time keyword that we can make this size variable. The key thing here is that there is no dynamic memory allocation that happens during the allocations. So again, I've truncated the body of append, pop, slice, and clear, but if you were to implement those, there's no dynamic memory allocation. You have no allocator, you have no way to do that. You should never use a global allocator. Never is maybe a harsh word, but you should definitely consider not using a global allocator, so you wouldn't even have one in scope if you were building this. The one thing I do want to say that is not captured here is we would handle the out of memory case when we add an item to the array list. So we would need something like if self.length is greater than or equal to the capacity, so we are essentially full and we try to add an item, we need to return like an out of memory error. Otherwise, we can go ahead and add the item to the array list and keep track of the length. Here's an example of how we would use the fixed capacity array list. This actually looks really nice. This looks like very clean Zig code and not very complicated to follow either. So you can see that we're creating our list. It's got a fixed capacity array list. The type that we're providing is an I32 and a capacity of 10. We're calling init, which if we take a look back at our initializer here, all it does is return self. Then we try to append some items. So we append 10, 20, 30. We can iterate over the items and work with them just like you would a normal array list. And we can pop items as well. Finally, we're just doing a standard debug print to show the remaining items. This approach is perfect for situations where you know the maximum size up front, or you can establish reasonable bounds. Let's extend this with a more sophisticated example. And unfortunately, this one's a little too big to put on the screen, so I'm just going to talk through it. What you could do is if you wanted to build a hash map, you could also build a fixed capacity hash map. I'm actually going to go back because you can imagine what this might look like if you were looking at a fixed capacity array list. It's very, very similar. So we have a comp time type, but with our hash map, we would have a comp time key and a comp time value, and both of those would be types. So comp time k, comp time v. Then we also have a comp time capacity, just like our array list. The structure is almost the exact same. We can get access to self via this, and we create a data structure to store our items. So the difference here would be that we are working with maybe something that wraps an entry using a key and a value, and then we would add that to our list of entries. The logic behind a hash map is a little bit more complicated than an array list, but the idea is still the same. You have to check the capacity and the length that you're working with to determine whether you can or can't do allocations that adjust the items that are contained within the map. So for example, if you were to create a hash map, a fixed capacity hash map of 25 spaces, and you have 25 items and you try to add another, you would probably want to return an error out of memory in that case, or something similar. It's not a specific type, so you could create your own error type that says something like hash map full or whatever, but you probably want to return an error case. The trade-off for these is that we need to know the maximum size at compile time. Thankfully, Zig has the comp time keyword, which allows us to specify variables in our code and use those at compile time. That solves that problem for us quite easily. For many use cases, though, like especially in embedded systems or performance critical code, knowing the maximum size ahead of time is a pretty reasonable constraint. Again, another example that might be a little too much to show on the screen right now would be something, well, honestly, more complex. So something like a JSON tokenizer can also be done with 0 allocations, which is quite interesting to think through. I'll give you that one for homework if you're interested, but you should try to come up with what a 0 allocation JSON tokenizer can look like on your own. Now I want to cover some advanced techniques and best practices for 0 allocation data structures. First, when you're building these or just trying to keep things off the heap in general, consider using a fixed buffer allocator instead of manually managing memory with something like the general purpose allocator or page allocator. This approach lets you use standard data structures, but with 0 heap allocations. It's often cleaner than building custom data structures. One of the nice things about Zig is that we have this generic allocator type. And as long as we're building our code properly and we're taking in a generic allocator, it's up to the consumer of that function to define how that memory is allocated. So they could choose to pass a general purpose allocator. They could choose to pass a page allocator. Or if they're really wanting to keep things off the heap and on the stack, they can create a buffer like you can see on the screen. And then they can wrap that buffer in a fixed buffer allocator and then get a generic allocator from the fixed buffer allocator. This means that, if they pass that allocator around, when that allocator is used for allocations, it will happen on the buffer, which is on the stack. That's pretty darn neat. So here are some best practices for 0 allocation programming in Zig. You should try to use the stack allocation when possible, especially for small fixed-sized data. You could prefer fixed buffer allocators for variable but bounded data. And try to use comp time for calculations and data structures that can be known at compile time. You can design APIs to accept slices instead of owning data wherever possible, and always try to handle capacity errors gracefully. Lastly, I would recommend benchmarking to ensure that your 0 allocation approach is actually faster. There are trade-offs to be made here when allocating so much on the stack versus allocating on the heap, and you might be shocked at what is or is not faster. All right, let's recap what we've learned about zero allocation data structures in Zig. So Zig gives you direct control over memory allocation. Fixed capacity data structures can be built using stack allocation, and we can implement complex data structures like lists, hash maps, and more without heap allocations, which is pretty darn cool. For real-world applications like parsers, you might even be able to find a way to do that with zero allocations too. Using fixed buffer allocator can kind of help give you the best of both worlds. So this poses a really good question. When should you use zero allocation data structures? Well, embedded systems with limited memory is the first thing that comes to mind. But you might also want to use them for real-time applications where allocation delays are just unacceptable. You might find a use for them in performance-critical hot paths or where predictable memory usage is required. And lastly, if you have long-running applications and you're concerned about memory fragmentation, a zero allocation data structure could help here as well. Thanks for watching. If you found this helpful, please like and subscribe for more Zig content. In the comments, let me know what other Zig topics you'd like me to cover in future videos. Thanks, and have a great day.